first, I'd like to know whether you hear us well from Chicago. Everything is okay for you there?
I hear you really well. It's a great connection. See you beautifully. Everything's great.
And so the idea is I'm going to first ask Ilan. Ilan is a student who likes to ask at least 10 questions per hour, so be prepared.
The best kinds of students.
Ok, here we go. Ilan, question number one. Alors vous vous levez, puis comme ça on vous regarde bien que la caméra, ça va zoomer un peu. Ça, c'est mieux. Allez, bon webinaire.
Hello. Good afternoon, good morning, whatever time you're at 5 o'clock. Yeah, we're morning still here.
Here for us, it's around 5 o'clock.
Yeah, it's 10 here.
So Your Inner Fish has been published in 2009, and 8 years passed since then. We all know that technology evolves continuously. New discovery happens every day. So we would be interested to know if there are things that you would rewrite differently since then, if things change for you in your mind, and are there some topics that have changed through these past years?
Yeah, that's a wonderful question, because as an author, you're always scared to read your work after it's been published because science, as you know, as your questions articulated so well, science is fast moving, and it's been very fast moving in these past few years. So there's a couple things I'd do differently, and there's a couple things I'd add. The one thing that I would add would be more on, in fact, chapters on the central nervous system, on the brain and nerves, and the workings and structure and evolution of the brain. Because in the last few years, molecular biology, some paleontology has come up to really show the deep antiquity. So your inner fish, even your inner fly or your inner worm, in the basic structure and wiring of our brain. And much of that has come from a new understanding of genomics. And so if I was to do anything differently, I'd add some chapters probably on the central nervous system. There have been a number of discoveries that have happened over the past number of years and new technologies that have really changed the game for us in a lot of ways. Two of them in particular. One is imaging technologies. So you remember from Inner Fish, the chapter where we discovered Tiktaalik, this thing right here. The chapter where we did that, somebody had to sit with a needle and a pin and vise and remove the rock grain by grain under a microscope. Now we have CT technology, high-powered CT technology, which can blast through the rock and give us images, detailed images of fossils inside the rock. So no longer do we have to physically remove it, we can actually image it. And that changes it in a lot of ways because we can now see inside the bones in a very key way. We can see the histological structure of the bones. We can see the structure of the brain case in ways we couldn't before. So that's a big one. Then the other big thing that I think would cause some changes in the book is the development of gene editing technologies. New technologies such as, I'm sure you've heard, called CRISPR-Cas, where we can now edit the genome and do experiments in ways that I could have barely imagined when I wrote Inner Fish in 2007. Now remember, the book was published in 2009. I actually wrote it in 2007. So, because there's the lead time between writing a book and publishing it. So, and that whole technology has changed too. And what it showed, with some work from my lab as well as from other labs, is the connection between fins and limbs is more surprising than I could have even imagined in 2007, 2009. That is, the cells that make our fingers actually make the fin webbing of fish fins, which is a total surprise, but that's, an inescapable fact when you look at the molecular biology. So yeah, those are the kinds of things I'd be thinking about. The good news is the basic structure of the book is the same. I focused on, deep historical discoveries too, as much as anything. And those are robust to the discoveries in the last number of years. So I think the core of the book stands. I'm always interested to write a new epilogue for the book, and I may do one in a year or two. It's just the publisher, sometimes they don't want to do that because they have books on the shelves that they don't want to, pull off the shelves.
Thank you very much. We just have a second question. It is, do you think that we will one day be able to find Luca, the last universal common ancestor? Or do you think we would maybe find a close version of it?
Yeah, I think it's a close. I think one thing about Luca we'll be able to do is to reconstruct it with great detail. Whether we actually find it in the record or not, I don't know. but we'll certainly find its signature in the record. And that signature would either be in one of two ways. It'll either be molecular in terms of fossils in the genome that emerge that we can predict from computational studies, or geochemical. That is, it will have certain metabolic processes that we could predict in advance that we should see in the geochemical record in the rocks of the Hadean or an Archean, billions of years ago.
I think it's Alexandre. C'est la question.
Hi, I'm just taking a
hello,
picture.
Neil. So
My students won't believe I was teaching a class in Switzerland, in Europe today, so I had to take a picture to show them.
In the first chapter, you talk about how similarities with the other species. For example, you said that we have the same limbs pattern, and it made me think about something. If I had to convince someone who doesn't believe in evolution, what should I say to him? What example or arguments should I come up with in order to convince him and show him the evidence?
Yeah, that's a fabulous
evolution?
question, because I deal with that all the time. So in the United States, we have whole portions of the country that are very resistant to science and evolution. And so this year, for instance, I went down to southern Mississippi, which is one of the places in the United States that is completely opposed to evolution in many ways. And I gave a talk on Tiktaalik. And what I like to focus on is evolution and science as a platform to discover and to make predictions. That is, and I like the story of Tiktaalik, this creature, because we were able to identify, knowing, where to find rocks of the right type, rocks of the right age, knowing the phylogeny and evolutionary history of the general creatures of this time period, we were able to predict where we'd find a fish with arm bones. So if I take people along that prediction and how we made that prediction, and then the years we spent looking for Tiktaalik, and then I pull out this, which is the arm bones of Tiktaalik, where it has a humerus, a radius, an ulna, and a wrist, and so forth, and I compare it directly to an amphibian. It's when you have when you have the story of discovery, when you have the story of the predictions that we can make in science, and then you pull out the physical artifacts of it, my arm and Tiktaalik's arm, it can turn some heads. Now, you're not going to always change people's minds. Remember, sometimes you're dealing with very deeply held beliefs, and those aren't given up lightly often. But what you can do is give people an appreciation for evidence. You can give people an appreciation for discovery. You can give people an appreciation for science as a platform for exploration and discovery. And once you do that, I think you enter a new phase of the conversation. You may not change everybody's mind, but you'll certainly open up a conversation that wasn't possible before.
Who's next?
Hello.
Hello. Ça marche, ça? Okay, sorry. It's a specific question in the chapter 1. Following the assumption that this book is aimed at people with average knowledge of biology and science in general, what is the aim of the precise description of the process and the difficulties of research?
Yeah, so what I wanted to do was to make the book less of a description of discoveries, but more a story about how we make discoveries. Because I think that's really important. Because when I teach science, we teach science really not as, you could teach science as a body of facts, here are the facts of science. But in reality, what science is, where it's most effective, is it's a way of knowing. It's a way of discovering, like I said before. And one of my goals was to capture that sense of discovery. And it was important, very important for me, at a personal level, to convey to people that science involves collaboration and teamwork. It's not just like I wasn't just out there alone finding Tiktaalik. I was part of a team. I was leading a team of really talented people. And it was that collaboration among people with different talents that led to the success. And that was important. And the other big piece was that failure is a big part of science. You know, we didn't just walk into the Arctic and find Tiktaalik. It took us 6 years of fumbling around. And we learned from our failures. And I wanted to give those lessons as well, that science is a, you know, it's a way of discovering, but it's also a very human enterprise. I mean, it wasn't, you know, just all fun and games. There were a lot of times I would come home and with nothing to show for myself. And I tried to give a snapshot of that in the book, not too much, just enough. That, you know, I didn't want it to be just a dry recount of here's what the discoveries are. I wanted to present it as much as a way of knowing as anything else and capturing that sense of exploration and discovery.
Who's next? Chapter 11? Chapter 2? Okay, so I will ask the next question too. In the chapter 11, so we make a big jump at the end of the book. In chapter 11, it started that we will possess a so-called thrifty genotype that will allow our ancestral body to save resources during times and of plenty so as to use them during periods of famine. And that is causes obesity, diabetes, high blood pressure, and heart disease in population with abundant and permanent access to food, as certain populations have today. Are we aware of any other characteristic of our genome which was useful when it was first positively selected, but that is harmful for
Sedentary
more
life, yeah.
sedentary, and less hostile environment? So, what other problem may arise from our pairing bias? For
Yeah,
example,
so there's a couple
50
things going on here. It's not only is our genome wired to process metabolically food in certain ways. You know, so lactose tolerance, for instance, the ability to digest milk, alcohol tolerance, alcohol dehydrogenase. These are certain genes that are present in some populations but not others, based on their evolutionary history. And so when you take those populations, for instance, that say may not have the alcohol dehydrogenase gene, where they can't process, because of history, alcohol as well as others who can, they face numerous difficulties, susceptibilities to cancers like esophageal and stomach cancer that other populations don't have when they're subjected to alcohol. Likewise with lactose intolerance. If you have populations that historically weren't, you know, lactose tolerant, and you put them into a, you know, into a zone where they're eating a lot of dairy, there's a disconnect there in terms of digestive diseases, particularly colon diseases and esophageal diseases. So those are two specific cases where in individual populations where they had certain genetic backdrops based on what the diet was, that when you place them in new settings, they are encountering new risks that their bodies weren't, you know, built to do. But more generally for us, you know, you think about the environment we live in. You know, the food industry has gotten very good, particularly the mass food industry, about figuring out what our tastes are. They can design foods that have the right texture, the right saltiness, the right sweets, the right fattiness to program our taste buds to want more of them. You couple that where we're getting very good at understanding our natural, you know, appetite-inducing sensations. You couple that to the fact that we're more sedentary in general than we were in the past, and that we have access to these, you know, very fatty, sweet, incredibly tasty foods that are programmed for us to be addicted to them. You can see what the nature of the problem is, where obesity is a problem in certain parts of the world. You know, so again, that's a disconnect not only between our present and past, but how in our present we're getting very good at tuning into, you know, our basal tastes and desires and appetites, you know, hardwired in our brains.
Hi. So we come back to chapter 2. You talk about limbs and arms and hands in general in chapter 2. So if you would have to create a limb and a hand in general, how would you create like the perfect hand? What are the flaws?
Yeah, so there's a couple flaws that are going to hand. You know, one of the biggest flaws lies in our wrist. That is, we have all the tendons And many of the nerves and blood vessels that supply our hands are going through a very tight compartment. Now, that tight compartment is there for an evolutionary reason, but that tight compartment, the carpal tunnel and others that are sitting here, really cause us problems. So if you have, repetitive action of the wrist and hand over periods of time, you and me and others are susceptible to certain inflammation and paralysis and numbness and so forth because those nerves are all going through a tight compartment. If I was to design it differently, I would probably have those nerves and arteries and muscles going not only through a tight compartment, but going in a much more efficiently designed compartment so that they're not all bunched together, so that when one swells up, it affects everything else in that compartment. So that's one case where our limb historically is not really designed for the kinds of things, the repetitive motions that we do today. And so that's just, that's because we have this narrow wrist with this one compartment that everything went through in ancestors, and there was really no selection before to get rid of it. So that's one case. But the limb design is actually quite, when you look at it as a flexible template for adaptation, it served as a template for bird wings, bat wings, pterosaur wings, modified in different ways, for flippers, for jumping arms. It's actually been a quite resilient design. Where it seems to utter the most stress is in humans that are sedentary, that have repetitive motions, that live longer than 50 years, all the things we weren't selected to do. And that's where this wonderful design tends to fall apart.
Thank you.
You made a lot of experiments in chapter 3, and we were wondering if you encountered any ethical issues with your experiments in general, because, evolution is a difficult topic in an ethical way.
So are you talking about the transgenic experiments where we would make transgenic frogs and mice and things like that?
Yeah.
Yeah, so that's an issue we deal with all the time. So and it's coming to the fore in a really big way, actually. So it's fairly routine to be able to take human genes and put them in fish, and put fish genes in mice. Their effects. To do that in my university, what you have to do is to apply for a permit. So we have a very strict animal care and use policy. So every animal care experiment has to have an application to this committee where we have to demonstrate clear clinical or potential human benefit to the research. And so when we made our applications, just like any lab does, when we did our applications, our goal in this really was to understand the foundations of bone pattern formation. How do bones get patterned during development? And the transgenic experiments, some of which were described in the book and some of which we've continued afterwards, particularly with the gene editing technologies, those are part of that. I think ethics comes into the bear. There's certain things you have to keep in mind when you propose animal research. One is animal suffering. The other is the utility of the research. 3 is how are you acting to minimize mortality during the experiment. So all those are continual issues we have to deal with. Those experiments aren't done just cavalierly. They're done with a lot of thought and consideration of the cost-benefit angle to each experiment. So. Yeah, it turns out for when you do these applications, the application for doing lower vertebrates, like for doing insects and things and fish and so forth, the bar is a little bit lower. Once you start working on mice and in particular primates, which we don't do in the lab, it becomes much more difficult, and there's a lot more strict protocols. You bet.
Hello. So it's a question about chapter 4. So since our diet is very different from our ancestors, how could our teeth and jaw evolve in the future?
Yeah, that's a really good question. And when you think about where we're evolving now, when you think about what humankind will look like in the future, that's a really good question. Because let's say all of us in this room were to take a time machine, and we were going to land in that time machine 30,000 years, 300,000 years in the future. What would people look like? Would there be people around? What would be the size and shape of their mouth, their jaw, their limbs, and so forth? And importantly, what's driving that evolution? So when you think about sort of the drivers of human evolution now, there's really kind of two kinds. One is sort of natural selection, Darwinian evolution, that sort of evolution that shaped our past. And if you look at the human genome, that kind of selection is clearly going on today. If you look at sort of our ability to metabolize certain foods, our resistance to microbial threats, you could see the signature of natural selection acting on our genome now. But there's another piece of this too that's really important, and that is that we as humans, through our technologies, our cultural practices, will affect our evolution as well. So for instance, traits that might be in one environment deleterious or even lethal, like say the inability to see well past 50 feet, which in a savanna plain is lethal, we can fix that with technology like glasses and contact lenses or surgery or what have you. So to get to your question, if you want to understand what the jaw and teeth will look like in 300,000 years or 1,000,000 years or something like that, I think it's hard to think that natural selection and evolution will be the only factor. It will be human technology as well. That is, there'll be new technologies for food and how we consume food. Certainly, that'll have to change. And there'll also be technologies that probably help us process that food. So it's a long way of saying that we're going to be impacting our evolution. And the kinds of teeth and the kinds of jaws that were so important in processing tough foods in the past certainly won't be as necessary going forward. So it's easy to guess that, perhaps we'll more slender jaws, smaller molars, which has been the trend in the human evolution for millions of years, ever smaller molars and smaller canines. It's not unreasonable to think those traits, that selection will continue. There's another layer to human evolution, just like every other animals, and that's sexual selection. What do mates consider attractive? And that could vary over time as well. So all these are things that will play a role in our evolution going forward. But it's not unreasonable to assume, and this is just a guess on my part, that the trends that have played a role in the past in our evolution, reduction of canines, reduction of molars, will likely continue in the future.
Thank you.
Hi. Could you explain the figure on page 106?
I don't know. It's been a long time since I looked at the book.
Uh,
Hold on, let me get a book. I haven't looked at the book in a long time, so let me see what figure that is. What's the figure?
It's about the place.
The organizer. Yeah, where you get the double frog. Got it.
Yeah. So we were wondering, why is this
Yeah.
place so important?
That's a really
What
good
is it?
question. So if you look in development at many organs, whether it's limbs or bodies or heads and so forth, there are usually these places called signaling centers where molecules that instruct cells what to become originate from. This is sort of a common mechanism used in development of different organisms, that there's a signaling center that is sort of the center that's set up early in development, and it is an active source of the production of proteins and other factors that diffuse across the embryo. And that diffusion across the embryo sets up a gradient of high concentration to low concentration, from which then cells can interpret where they are in space. So it seems to be that this is one mechanism that development uses through evolution to be able to tell cells what to become in space by setting up these different gradients. That's sort of the classical explanation for why you have these signaling centers. And it still seems to hold to some extent. And that's, You see a signaling center in limbs, that ZPA, which I talked about with Sonic Hedgehog. You see it with the organizer in the early embryo. You see it in the brain. There are multiple signaling centers there. And in each case, you have molecules that are sort of setting up a Cartesian coordinate system, more or less, of gradients, where cells then can read out where they are in space and develop accordingly.
Okay, so hello. In chapter 7, you speak about an experience with an algae which is unicellular, and then when you put a predator, then it becomes a body. So, do you think that it's really how it happened, like in the history of humanity, like that maybe some of the unicellular became?
Yeah, that's a good point. So, yes and no. So I included that example to show not necessarily that predation was the main reason why we have bodies, although it could be one, but to show how easy it is to generate a body from unicellularity. So there have been a bunch of experiments that people have done in the last 15 years. One is the algae experiment. People have also done it in yeast, where they've gotten unicellular yeast to form a kind of a body. And again, they've done it in response to predation, in this case, to get bigger or protect their cells. So when you think about the factors that are behind the origin of bodies, there are a couple of them that are prominent. One is that maybe it's not just to protect themselves against predators, but maybe it's to become a predator themselves, a better predator. So they could be on both sides of this equation, being better predators, but also protecting themselves in another way. But what that example shows really well, and others like it, which I didn't include in the book, were the shift, this huge shift when you think about it, from unicellularity to multicellularity, is not that hard a barrier because creatures can cross it all the time under the right conditions. And then what that means is then you need an evolution to ask for what are the right conditions upon which this shift can happen. And then, extrapolating back to 600 million years, or 800 million years, it becomes clear that having high levels of oxygen, having broad, diverse communities of microbes that already have the mechanisms to build bodies inside, they're using it for other purposes. And then simple shifts. It could be predation. It could be protection from UV radiation. It could be protection from oxidative damage from oxygen in the elevated levels of oxygen in the air. All these things together probably add up. And as your question suggests, that predation in evolution is a very powerful force, and it's hard to rule it out as a possibility in this case for the origin of multicellularity.
Hello. In chapter 8, you talk about smell and olfactory genes. And you say that we most likely traded some of our olfactory genes for our vision. So I wanted to know if it's the same for birds like owls or...
Yeah, they can smell, but it's not as keen as us. They're truly optic animals. Their battery of olfactory receptor genes are actually much smaller than mammals. And they are keen visual predators. So they're, like, as your question suggests, that they're heavy on the sight end of things, extraordinarily so. And you think about what a bird does. Not all birds are like this, but what a bird often has to do, particularly a predator that flies and is a predator for ground-dwelling animals, they need incredibly acute vision. And sense of smell is probably not as important because they're very distant from their prey. So when you think about this sort of constellation of selective factors acting on, say, a raptor that flies high, and in particular one whose prey is on the ground, they're optimized for sight, not for smell, in a very big way, as you point out. And so, yeah, I mean, I think mammals are interesting because mammals are primitively smelling animals, and then we began our mammal past and then became very visual primates, So we carry some of that mammal past inside of us in our olfactory genome, but those are dead genes. They're fossil genes that don't work. They're just sort of still there, but not functional. Birds don't have that. You bet.
Thank you.
Good morning or good afternoon.
So, hello. We just have a general question about the 3 chapters we read. Was chapters 8, 9, and 10. It talks about the senses, and we wondered why didn't you we wondered why you
Yeah,
didn't really
so there was a
mention
lot going on with that. So for the senses, when you think about vision and olfaction, there was not much to say at the time about Tiktaalik. We had just discovered Tiktaalik. Remember, we discovered Tiktaalik in 2004. The first papers were published in 2006, and I was writing the book in 2006, 2007. So we were still in the early days of trying to figure out Tiktaalik. I mean, we were really kind of mostly focused on the limbs, and so part of it is how science works. We were working on the limbs first and the head, and it was really only later that information about the sense organs came in. We didn't really know what say take hearing, for example. We didn't really know what that part of the brain case in Tiktaalik looked like until 2009, when the book was already in the press, 2008, 2009. The book was already well in the press. And what's interesting here is that the skull of Tiktaalik, the zip, or a cast, has this bone right there. Where is it? Where is it? Where is it? Where are you? There, right there. That bone right there. And on the other side, that bone right here. That bone right there. That's called the hyomandibular. When you trace that bone, you can trace that bone from basal lobe-finned fish like Eusthenopteron. You can trace where it's really big. You can trace Tiktaalik where it's smaller, and then you can trace it to Acanthostega and other tetrapods where it's tiny and it's a stapes. So this is a gill bone that gets transformed over time from big, smaller to even smaller to become the stapes in hearing. In Tiktaalik, it's not used in hearing. In Tiktaalik, it's used in chewing and in breathing. So the shift from, one of the big shifts from Tiktaalik to creatures like, Acanthostega and Ichthyostega, which are true tetrapods, is the shift of that gill bone used in feeding and breathing to hearing. Now, we didn't know that till 2008, 2009, right? I mean, that was a story we only published after the book was well into press. That's the example. The thing about smell and sight in Tiktaalik is we really didn't know a whole lot. We actually don't know still how to reconstruct what the olfactory receptor gene, repertoire was in a creature like Tiktaalik. We can only infer it from coelacanths and lungfish and looking at those situations. With regard to sight, there was a paper published about 5 months ago looking at the origin of tetrapod vision. So one of the big shifts as you go from water to land is you're changing the sensory environment. That's what your question is about, obviously, and it's a great question. One of the big things to change is they actually go from having, so Tiktaalik actually has sort of smallish fishy orbits. They're not huge. When you get to early tetrapods, they get huge orbits. I mean, they're much greater bigger holes on the skull on either side. And so that's a big change here. We really didn't know that when we published the initial papers. We didn't have. I mean, we should have. I mean, it's pretty obvious, but somebody else pointed it out. And it was a really brilliant observation.
And so the following question concerning also the senses is, you talk about vision, smell,
Yeah,
and
touch
also
and taste.
sight, but
Thank you. Yeah, so touch and taste. So touch and taste, again, those were 2 senses, and there's others, pain, proprioception, and others. There were a whole bunch of senses I couldn't get into because we really didn't understand them from a comparative sense. So the senses that I sort of focused on were the ones where we had the most comparative data on. Now in the last, say, 3 or 4 years, we've learned a lot about touch. We've learned a lot about touch in primates and people. We still don't have a really good, clear sense of the sense of touch in flies and worms and even in fish to the same degree. So in writing the book, my criterion for including something in the book was having a good basis of comparative knowledge, whether it's of the genes or the anatomical structures and so forth. So when I applied that criterion to the different senses, that's why the 3 senses popped up that I talked about, not the others.
And while you were talking also about flies, there's an experiment that you did was, for example, if we had an extra eye, would it be as functional as the two normal ones? Since
Yeah.
the experiments on the fly show that is possible. So if we had an extra
Right.
eye,
That's a good question.
how would
So, I mean, if you think about, so you can generate, Walter Goering generated and his colleagues, Geneva generated, eyes everywhere, right? They were able to take PAC6 and its equivalent and generate eyes on limbs, eyes on wings. The one thing those eyes didn't have is they weren't wired to the brain. So you had the eye tissue, but you didn't have it wired to the central nervous system like a regular eye. Now, you could. I mean, if you had that in the right place, you could get a functional photoreceptor that is wired in some general way to the brain. It's possible to do that. In fact, we have there's other visual organs that exist that aren't in the head of many creatures, and they're used in many different ways. So, for instance, one creature, so scallops, for instance, live in their shell, but they have a lot of eyes that exist, in the front end. Octopi or cuttlefish, they have photoreceptor cells on their limbs. So they're on their limbs are loaded with little, quote, eyes. And those are used to detect the external environment and adjust accordingly. If you've ever seen just type in octopus camouflage, it'll blow your mind what they can do. They can sense their environment and adjust accordingly. Well, the way they do it is they have eyes, or a version of photoreceptors on their limbs and across their body. So there are examples of extra eyes, if you will, across the different bodies of different animals. And we can induce them as well. I mean, when you think about a third eye, you can think of the pineal in one sense. People have called it a third eye. It's in some animals, it's a whole, well, Tiktaalik has one, right there, that hole right there. And that's a third eye, if you will. It's a photoreceptor in many animals. And it's used to sort of tune the animal to the circadian clock, to the light-dark cycles that exist.
And also, since you were talking about predators not necessarily needing, for example, smell, what would happen if we lost also our sense of smell? Since we're not really considered predators, but more of...
Boy, eating dinner and lunch would really be boring. I mean, sense of smell is so much part of our taste. Think about when you have a cold. So really only have about, when you think about when we taste food, and when we can tell the difference between healthy food and unhealthy food. Take rotten food. All right? If we don't have a sense of smell, food loses its taste, right? The reason for that is there are really only 5 to 7 basic tastes that we can pick up. But we can pick up a zillion different smells. So the taste sensations that we have are as much a product or more a product of our sense of smell than our sense of taste on our tongue and our palate and so forth. So the challenge there is if we lose our sense of smell, we lose really a lot of our taste, which tells us good foods from bad foods, but also safe foods from unsafe foods. When you think of like a rotten food or spoiled milk or something like that, the only taste cue you would have to something like that is salt or sour or umami or one of those things, or sweets. And you're not going to be able to tell. So if I gave somebody like really spoiled milk, if you had a sense of smell, you wouldn't even put it to your mouth. Whereas if you don't have a sense of smell, you'll put it to your mouth and you'll take a few gulps and you're like, oh, that's kind of sour. You know what I mean? That kind of deal. So I think when you think of our full sensation of taste, which actually serves us very well in detecting harmful from safe foods, sometimes, not always, but sometimes, I think smell's a big part of that. And that would, losing that would not only would it not be fun eating food, but it would be probably dangerous.
Hello. So in chapter 10, you explained that the inner ear is responsible for telling us which way our head is tilted or how fast we are going. So if the inner ear is removed, would we, with the help of vision, would we still be
Not as easily, no.
to tell
What'll
what's
happen, what
going
typically
on?
happens in humans that have sensory defects, so in blind people or people who lose their hearing or lose their ability to detect in their, in their vestibular system, we're very good in our brains about finding alternative ways to perceive things. You think about a blind person who can detect sounds or vibrations almost in a way that gives them a form of sight, if you will. We're very good at that. And so with a sense of orientation in space and a sense of acceleration in space, there are other mechanisms that we could use. You think about the stretch receptors in our muscles. You think about the touch receptors in our skin. Those things can also be used to determine our acceleration or position in space. And so, to some extent, the brain will rewire to some extent to allow that. Will it be the same? No. Will it compensate in some way? Probably yes. But how much, I honestly don't know.
Okay, so hello again. Throughout the book, we notice some displays of more anthropocentric point of view, as the images in page 9 and the one in page 183. In fact, we were told that any suggestion of hierarchy in evolution was a problematic and wrong approach to theory of evolution as a whole. So this displays
Of course, yeah. So there's a difference between hierarchy and evolution, which is real, and progress. They're very different concepts. So there's definitely a hierarchy in evolution in the sense that as evolution happened, ancestors gave rise to descendants. And those descendants gave rise to ever more descendants. And their descendants gave rise to ever more descendants. So when you think about the hierarchy we talk about in evolution that makes sense, it's like the family tree hierarchy. A hierarchy from grandparents to parents to kids to cousins and so forth. So when you think about a family tree, just take any of our biological families. If you think about our biological families, there are great-grandparents, great-great-grandparents, great-great-great-grandparents, but there's a hierarchy based on those generations, right? And so the hierarchy I'm talking about that's most effective in biology is thinking about that family tree hierarchy, from the generations that not only exist in our families, but extending that back to the generations in our evolutionary history. So you can look at that history we share with worms, you can look at that history we share with fish, you can look at that history we share with things we call amphibians, things we call reptiles, mammals, primates, anthropoids. You can follow that rhyme, and that's a hierarchy. That's a hierarchy of phylogeny. That's a hierarchy of classification. That's a hierarchy of common descent. So when we talk about that hierarchy, I feel very comfortable with that because that reflects what we know. Where I'm less comfortable with I think this is where you're going, is the sense of progress. That somehow there's an inexorable drive for progress in evolution, which people have wrestled with over the century and a half, and it's a very challenging concept. With regard to the book Inner Fish, it was very specifically focused on humans, and there's a reason for that. The reason was I wanted to show people that inside of us are artifacts of of 3 billion years of history. So what it did mean is that I had to put humans front and center. I mean, I could have called it your inner fly, your inner worm, and it's all about showing our common history with different groups of creatures. But I could have written a book, and I said this in the notes at the end. I could have called this book Your Inner Human and written it from the fly point of view. I could have called it Your Inner Frog, Your Inner Human, and written it from the frog point of view. So it's just a matter of perspective and evolution, but I was explicitly thinking of humans in this book because, honestly, I wanted people to see their bodies in a different way. That's the kind of the hook to the book. rather than work through a very general evolutionary story, I wanted to make it very specifically and personal about us.
Thank you. So does anyone have another question? No?
That's it?
Yeah.
Somebody wants to ask me a question on page figure 109 with oxygen tissues, I guess this one is not really important. Someone can do that? Or I can do that if you want. Oh, you want to do it? Someone else want to do it? Who wants to do it? Quentin want to do it? Okay, so go on.
Oh, hi. So I have a particularly personal question. So I suppose you're aware of the ongoing debate which opposes the conservatist Christians and the evolutionists as for what concerns evolution. So what I wanted to know was what was your point of view as regards your point of view towards this situation and what position you would take.
Yeah, that's a very good question. It's something we really need to confront, particularly in recent days. I should say, when you look at sort of religion and science and their position on evolution, a couple things to consider. Not all of religions have problems with evolution. If you look at the Catholic Church, if you look at most Protestant branches, if you look at Judaism, most moderate Islamic branches, there's no stated challenge of evolution. In fact, I spent a week at the Vatican in a conference run by the Pope, and I gave talks on the history of life, and this was in February. And the Catholic Church, from the Big Bang to evolution, no problem. There's a strand of Christianity, but also Judaism as well, and some Islam, the more orthodox style, which take a very literal reading of Scripture. Now, if you take a literal reading of Scripture, and every word is truth, it leads you to a number of positions, some of which are kind of challenging, but the most challenging is the age of the Earth, obviously, right? And the sequence in which the origin of the Earth and universe and Earth and life happened. And so that is a particularly challenging viewpoint because in that literal reading of Scripture really stands in contrast, and if you take it extremely literally, which some people do, it stands in a challenge not just of evolution, but of geophysics, of physics, of chemistry. It's about science as a whole. I should say a few years ago, I went to Kentucky, and I went to the Creation Museum. There's a Museum of Creation Science, this whole viewpoint. Very popular museum, and it's really amazing how they set up a completely alternative worldview. And the way they do it is to open it up by saying, well, there's two ways of knowing. Their way of knowing is, God's truth, the revealed truth of the Creator, and then the other way of knowing is, man's rationality. And the argument that they say is that, well, man's rationality is inherently flawed. God's truth is eternal and inherently true. And then they set up a whole, cosmology and epistemology around that. Having a conversation in that regard, and I do this all the time. I mean, I'll go to, South Carolina, I'll go to Alabama, I'll go to Mississippi, as I said earlier, Oklahoma, southern Texas. I do this a lot. And go to those communities and have a very respectful conversation. I'll bring Tiktaalik. I'll talk about how we found Tiktaalik. There's an earlier question that happened in the back. And focus on the discovery story. And then to talk about, okay, well, how either you believe that a creator is intentionally deceiving all of us by planting these fossils in this sequence, or you believe that what we are is able to figure out what happened in the distant past. And once you open a conversation like that, you may not necessarily change their mind, but you open up a conversation. And anytime you can open up a conversation with somebody, particularly somebody who has a heavily hard-held, deeply held religious view, as long as you're respectful of it, you can have a conversation. And some people's minds you're not going to open up to science. Others you will. And that's just the nature of the conversation we're in now.
Okay, thank you.
Okay, So we learned that if we evolved, it was also because some animals in each species were better adapted, and that they were, for example, less killed, and so that the ones that had characteristics which permitted them to survive, reproduce more, and so more of these characteristics. Yeah, in the offspring. Comment on dit perdurer? Non, comment on dit? Yeah, were maintained. And so with all like the medical stuff that we have and that permits us to live longer, how are we going to evolve? Because if we, like, even people which which have less good characteristics to survive can be helped by medicine, how are we going to evolve?
Yeah,
And
that's
why?
this is like what I was saying earlier. I mean, technology sort of changes the game. So many genetic traits, which in our evolutionary past would be harmful or lethal, now aren't. You know, so, and they're not going to be. So one of the things to keep in mind is most genetic traits, their fitness, their, you know, how good they are or how bad they are is really dependent on the environment that they're in. So some traits are lethal in certain environments and they're neutral in other environments. And it depends on a lot of things. Well, technology changes that. So the trait of, for instance, myopia, nearsightedness, the trait I have of extreme nearsightedness would be lethal if I just lived in the savanna plains without eyeglasses. Yet it's neutral to me because I wear glasses or contact lenses, and in the environment I'm in, it's kind of meaningless. It doesn't really kind of affect anything. So when you're thinking about traits, genetic traits, whether they're good or bad, it really depends on the environment they're in. And what we as humans are getting very good at doing is changing our environment, right? And so as your question suggests, what that means is our genome collectively will be loaded with traits, or already is, loaded with traits that in the past would have been lethal and killed us. But we're still carrying them, and our children and grandchildren will carry them. And the question is that a good thing or a bad thing? And my point is it's just a thing, because it's neither good nor bad, because if technology makes those traits neutral, then it's not really a terrible thing, right? One thing that's clear, and I was at a dinner last night in Chicago downtown, and we were a scientific dinner, and somebody was going through some calculations basically saying children that are born today have a very high likelihood of living to 105 and maybe even 110. Just because of the technological changes. You know, and certainly those children that are going to live to 105 and 110 on average, they are going to have all kinds of factors in their genome which in the past would have been deleterious or lethal, but don't matter anymore, right? And so, I mean, and that's the thing. So we as humans are very good at changing our environment, right? Through technology, through cultural practices, through education and so forth. And I think those are going to be the operative things going forward, less whether we have good genes or bad genes.
So do you think that we are going to evolve or not?
Oh, I think that we're definitely going to evolve in some ways. I mean, we're continually evolving in some ways with regard to the war our genome has and our immune system has with pathogens, with viruses and bacteria and so forth. So, you know, we live in a balance of microbes, right? The microbes inside of us, the microbes outside of us. We live in a very finely tuned balance with them. And when that balance goes awry, then things fall apart for us. So we're very much in tune to that. That's part of our evolution. And I think that's clearly going to be a piece of us. And there may be more anatomical traits that change over time in an evolutionary way. But I think mostly if you're going to look at human performance, if you're going to think about how long humans live, how smart we are, how fast we can run, you know, how well we can, you know, do particular tasks, human performance going in the future will be as much driven, or if not more driven, by sort of technological advances than, say, Darwinian evolution, I think. Just look at what's happening now. And look at how, take bicycle racing, for instance. You know, I mean, it's almost like you need two different statistics, those people who are doping and those people who aren't doping. And just imagine as we enter a phase of the world where we can actually edit the genome, which is something that's possible. You know, do we need two sets of statistics for, you know, people who've been CRISPR'd and people who aren't CRISPR'd, you know, for gene edited and not? I mean, these are all questions we have to deal with as a society, and because we're getting very good at affecting our technologies that impact human performance.
Ok. Encore une, deux.
In relation with the last question, I wanted to know if you think that maybe there's some of cleavage that will appear in some years because in different part of Earth, the environment isn't the same, and they like in
right.
poor countries, they don't have technology to help them survive even when they have like some handicaps. And will there be a cleavage between rich countries
That's
and
fabulous,
poor
yes.
countries, maybe?
That's a great point. So there are two things to consider as we talk about technology. One is not just the development of technology, but the other is access and the social practices that bring that technology to the culture, the socioeconomics and so forth. So if you look, as your question points out so well, if you look at certain parts of the world, life expectancy is 52, 53, not 78 to 85. And so it's not just technology, it's access to technology. And you can imagine a world where we have a world of have and have-nots for technology, where we almost have, in terms of human performance, great variation, not based on our biological capacities, but based on the access to technologies that enhance or change human performance. That's true to some extent, but the other point to keep in mind is that technology almost inexorably gets cheaper and more widely developed over time. And so, you know, as technology expands, take computers or take even cell phones, they proliferate. So when you take sort of like the technology that impacts a lot of people's lives nowadays are cell phones. If you go, you know, around the world, even to very poor places, cell phone technology has proliferated very dramatically. And there are a couple factors at work here. One is that technology gets more powerful over time, but technology can also get cheaper over time. Just think about what happens to computers and things like that. So I don't have the answer here. I'm just offering some points to consider. One point to consider is that it's not just technology, but access to technology. But the other piece is how technology itself evolves, is it tends to get more powerful and cheaper over time. So what that means is we might have two different competing forces between, you know, forces which would serve to restrict the access of technology based on socioeconomics, cultural practices, and so forth, and then forces which tend to democratize technology, which include its, you know, the way it gets cheaper and more powerful over time. You bet.
Thank you.
Hello. In the back of your book is written, "Why do we look the way we do?" But isn't it more, how do we look the way we do? Like,
Okay, so there's two, yeah, so you're getting very Aristotelian on me here in terms of causes. So take the Aristotelian causes, final and proximate causes. So why and how? So how we look the way we do is basically following the evolutionary sequence. So I could say, you know, here's how we ended up looking the way we do. But there's another way to say is that, you know, why we look the way we do is in large part due to the history we share with the rest of, you know, with life. Why we have two eyes and not one in the middle of the head. Why we have two nostrils. Why we have most of our sense organs in our head rather than in our tail. Why we don't have eyes in our limbs like a cephalopod. You know, and that's as much an explanation of history as it is anything. So the thing we were trying to explain is, you know, that history is a deep part of us. It's a deep part of the way we look. It's how we function and so forth, and it can't be ignored.
Okay. But like the why is not because there is a purpose.
No, not at all.
or
I mean, no.
it's
I don't
more,
think I don't think we were ascribing a purpose to anything in the book. I mean, we were ascribing we were ascribing it to history, more history than purpose.
Um, so I was thinking about the fact that today well, evolution is a question of maybe technology and not only biology. And my question was about do you think that maybe one day human will maybe they will have a limit
Yeah.
in evolution? Maybe that one day
Right. You
they
think
will
about
have
it. So this is a big area of debate right now, and so it's particularly among researchers who work on aging. Is there a maximum lifespan for humans? So let's say we get very, very good at recognizing, detecting, and curing cancer. Let's say we get really good at conquering infectious disease. Let's say we get pretty good at understanding neurodegenerative diseases. You know, these are the main things that happen with aging, right? Susceptibility to cancer, susceptibility to neurodegenerative diseases, and so forth, and cardiovascular issues. Let's say we get really good at that. Is there a maximum sort of physical limit to how long people can live and live, not just, exist, in a box, but have a functional life of well-being, a fulfilling life, because that's a challenge. And people are pretty divided on that. I mean, some people have said that, the maximum age, even with technology, that people can live is about 135, 145 years, somewhere in that. And the argument being is that if you just look at the property of our cells and the material structure of them and how they divide, and if you look at the property of the chromosomes that gives rise to cells, that there's a limit. So I don't know the answer here at all, honestly. But, the one thing that we have to keep in mind always as we enter the future and as we enter an age where we can extend human life, it's not just the amount we live, it's the quality of life. And, when you think about the greatest challenges we face as our societies, whether it's, North America or Europe or Africa or Asia, it is as we get better in extending lifespan through cultural practices, technology, or what have you, we are going to have an aging population, and an aging population means that we have to be very concerned about the quality of life, not just the duration of it. And that's anybody who's had aging parents knows this all too well.
Thank you.
All right.
All righty.
So I think that's it. Thank you very much.
So I would just like to finish this pilot event by thanking Neil Shubin for his participation. Thank for his time and for the very food for thoughts that he provided. And thanks also to all the students to preparing this wonderful discussion. The event was supported by the Swiss Science National Foundation and bringing here by the University of Geneva from the platform of Science Communication, Beauty and Science Breaker with the collaboration of Pierre and the high school Collège Rousseau here in Geneva. So once again, thank you very much to everybody. Thank you to Neil. Thank you to the students. Thank you to Pierre. And I hope
Thanks,
this was
everybody.
the first event of a long series. Thank you.